Alright, welcome everybody. So today we're going to talk about some reactivity of alkanes. And to do that, we are going to discuss a few different types of reactions and also discuss their stability. And you wouldn't really think that alkanes were stable per se because of the bond between the carbon and carbon, only being a single bond, but it turns out that they happen to be extremely stable, and we'll discuss why in a little bit. We'll also discuss how they combust in air using oxygen, and we'll also talk about specifically this free radical substitution reactions that occur, these homeolytic substitution reactions that occur, and we'll talk about the mechanism, the steps, and I'll introduce something to you called the curly arrow, and the curly arrow is sort of this way of showing how electrons move around. Okay, let's talk about combustion of alkenes first. So the alkenes, when we have them, they're generally really stable, as I mentioned before. And we'll talk about, why this is the case. And this is one of the main reasons why we use alkenes as a fuel. It can be stored relatively for long periods of time without, actually going bad. It's also, stable when you are driving a car. If, God forbid, you're in an accident, although it is flammable, it's not nearly as reactive as some other fuels. So, your car necessarily won't light on fire, and you won't, have this crazy explosion unless, that gas is ignited. The general idea for combustion of an alkane is that you take the alkane and you add oxygen to it. And that oxygen will react with the alkane, and you'll produce carbon dioxide and water. And this reaction should be pretty similar to what we had last year. So, for example, if we were to put in a real example here, we could have something like C3H8, propane, plus oxygen, and we'll form CO2. Excuse me, let me just delete that. CO2 and H2O. The only thing that's really required is to just balance this reaction. So if we balance this reaction, we're going to need 3 carbons for the CO2, we're going to need 4 waters to balance the hydrogens, and we're going to need 5 oxygens to balance the rest of the equation. And so there we have our reaction of alkene with oxygen. We're forming carbon dioxide and water. That's considered a complete combustion, though. What if we were to have like an incomplete combustion? And so when we have an incomplete combustion, that means that the oxygen in the reaction is limiting. And so you can see the myriad products that you can form here. We have forming just carbon, carbon monoxide, and some carbon dioxide, as well as the water. And if you've ever had one of those ugly yellow flames and then it is against a glass beaker, it'll form this layer of carbon deposit on it. This is how some engines get that carbon deposit. They don't run as well. They're not optimized. They're not getting enough oxygen into the intake. Carbon monoxide is CO, that poisonous gas that's produced when you have inefficient burning of fuels in your home. And so that's why you have those carbon monoxide detectors. So they help to detect the carbon monoxide, and this way you do not breathe that in. The carbon monoxide is very toxic. It'll bind to the hemoglobin in your blood, and it will replace the oxygen, and it will basically effectively suffocate you from inside out. Okay, so let's talk about the stability of the hydrocarbons. So, there are at least 2 reasons why we can think of the alkenes as being non-reactive. And one of them has to do with this, carbon-to-carbon bond being relatively strong. Although the carbon double bond is stronger, it's actually more reactive. This CC bond, it only has 2 electrons between it. And so because of that, there's generally this low repulsion of electrons. So you have this low repulsion of electrons here, and that low repulsion causes that bond stability to increase. If you start with something like an alkene, where now you have 2 sets of electrons, this has a higher repulsion. This leads to a decrease in stability of that bond, despite the fact that it takes more energy to break that bond apart. So when we have a hydrocarbon that is an alkane, the molecule is relatively stable. It doesn't react with things. The other thing is that this molecule is nonpolar. And we know that when you have nonpolar molecules, the reaction tends to be slow. And this is in part due to the fact that it is insoluble in water. The insolubility in water is due to the fact that there's no hydrogen bonds that can form. And so you have this insoluble hydrocarbon in water, and so there's no ability for there to be some kind of charge interaction where hydrogens could be ripped off and bonds could be broken easily. If you think about an acid, by contrast, an acid can easily dissolve in water and then very quickly react in the aqueous form. So let's talk about this first type of reaction that's really important. It's halogenation. It's a substitution reaction. So this is a substitution reaction in which we are substituting the hydrogen in ethane, for example, with a chlorine. And they show that here. So now one of those H's has been replaced with chlorine, and we get this hydrogen chloride gas out. So this is occurring only under the case where we have ultraviolet light. If we put chlorine and ethane together without some sort of source of ultraviolet light, then we won't get this reaction occurring. It won't happen. So with the UV light, that provides enough energy to break the bonds in the hydrocarbon and in the chlorine, and it allows for you to get this reaction. So let's go through the steps for this. This is called a free radical substitution because a free radical is formed. And you might be saying to yourself, well, I've heard this term free radical, but really, what is a free radical? And we're going to look at that here. So this is a free radical is this species where you have an unpaired electron. You have a single electron. And it's kind of messed up on my slide, but what's happening is the Cl here, and this is where these curly arrows come in. If we were to draw this actually with two dots to show the electrons, so we have Cl and then the electrons. When we shine UV light, those photons are powerful enough to break the chlorine bond, and so one of the electrons here will leave that bond, and the other electron here will leave that bond, and what you'll get is you'll get Cl with an unpaired electron. Now this free radical here is very, very reactive. These arrows that I draw show the electron movement. This is called a homolytic fission, and that is because you're breaking it equally into two equal atoms that have, or two free radicals, each with the same number of electrons. So now we show this here, and this first step in this reaction is called an initiation. This is where the radicals are actually formed. The next step that takes place is something called a propagation, and you should know these steps by heart and be able to, recognize them. This propagation step is a step where, the free radicals are kind of propagating, feeding each other. And so what we see is that this free radical here, this chlorine, will attack the ethane in this case. And that produces a new free radical and the HCl. Now this free radical that formed, which we can highlight again in green here, then goes and reacts with another chlorine. And then we will produce our product. Now this chlorine right here, this will actually go back and react again with another ethane. And so you get this kind of chain reaction, this propagation. Now every once in a while, the two chlorines will come together. So you'll also get this going on, where those two chlorines will come together, and they will form the product of Cl2. But if we have more UV light, then we can start again going back to the beginning. But this is a termination process. This is where any two radicals combine together. You could also have this situation here for a termination, where you have the C2H5 and you have one of these chlorine free radicals. And in that case there, you have another termination where you get the product that you want. And then you could actually have a situation where you're making some butane, where you have the two free radicals from ethane coming together. The idea is to keep the concentration of the things that would terminate the reaction low. So we could go through thousands and thousands of these cycles, these propagation cycles, until we actually reach a termination. We don't need to use chlorine. We could use any halogen we want. And the alkane can be substituted again and again and again until you get a fully substituted, with in this case 6 chlorines. So the things I want you to take home from this particular video is, one, the alkanes are unreactive. They release a lot of energy when they're combusted. They're also stable. It makes them good fuels. They undergo this free radical substitution. They form the halides and a hydrogen halide in the presence of UV light, and you need to know the mechanism. Know the mechanism, free radical substitution, know the steps, memorize it. You need to know it. It's on the test. Alright, so next time we'll do lesson 5, where we talk about more reactions. Alright, thanks so much for watching.